Good morning. In this video, I am describing the inorganic chemistry chapter Chemistry of lanthanide elements. From modern publishers, published by Dr. SP Jauhar. We have learned that the elements in which the last electron enters the f orbital of their atoms are called f block elements. In these elements, the last electron is added to the third to the outermost, called anti-penultimate energy level n-2f. These elements are called inner transition elements because these constitute transition series within transition series D block elements. They consist of two series of elements placed at the bottom of the periodic table. These two series are formed by the filling of electrons in 4f and 5f orbitals are called lanthanides and actinides respectively. The series involving the filling of 4f orbitals following lanthanum, whose atomic number 57, is called lanthanide series. The elements present in the series are called lanthanides. There are 14 elements in the series, starting with cerium of atomic number 58, ending with lutetium have atomic number 71. The name lanthanide is derived from lanthanum, the first member of the series. These lanthanide are also sometimes referred to as lanthanons. All these elements have closely similar properties and therefore are considered together. The reason for their similar properties is that the 4f orbitals in which the electrons are added or embedded in their inner shells, while 5d and 6s electrons, which have similar configuration, are exposed more to the surroundings. Because of their similar physical properties, their separation and identification proved to be very difficult task. The first stage of in their separation was to get them as oxides. However, the occurrence of the oxides of lanthanides was very rare. Therefore, these elements have also been called rare earth elements. Nowadays, the term rare earth is not used. Their substantial deposit occurs in USA, USSR, and India. General characteristics of lanthanides. The important general characteristics of lanthanides are discussed below. First, electronic structure and position in the periodic table. The lanthanides involve the gradual filling of 4f orbitals. It may be noted that the energies of d orbitals and the next inner shell f orbital are closely similar, and therefore the order of the filling of the 4f orbital in the atoms show quite irregularities. At lanthanum have atomic number 57, both 5d and 4f orbitals become stable due to increased effective nuclear charge as a result of the poor shielding effect of 6s electrons. Therefore, it is observed that at lanthanum, the incoming electron enters the 5d orbital and its electronic configuration is xe 5d1 6x2. However, as we move further after lanthanum, the energy of 4f subshell becomes lower than the 5d subshell, and therefore the next electron in cerium enters the 4f subshell. The electronic configuration of cerium is 4f2 6s2. The filling of 4f orbital continues till we reach ytterbium, in which the 4f subshell gets completely filled. Ytterbium electronic configuration is 4f14 6s2, and lutetium electronic configuration is 4f14 5d1 6s2. This constitute lanthanides. The general electronic configuration is written as xe4f0 5d0 6s2. The electronic configurations of lanthanide are given in table as elements lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium is the series of the lanthanides, and the symbol is La is the lanthanum, cerium Ce, praseodymium Pr, neodymium Nd, promethium Pm, samarium Sm, europium Eu, gadolinium Gd, terbium Tb, dysprosium Dy, holmium HO, erbium ER, thulium TM, ytterbium YB, lutetium Lu. Second, physical properties. The important physical properties of lanthanides are given in table 2. These are discussed below. First, ionization energy. The lanthanide have fairly low ionization energy. The first ionization energy are of the order of 560 kilojoule per mole, and second ionization energy is 1150 kilojoule per mole. These values are quite comparable to alkaline earth metals, especially calcium. Melting and boiling point. Lanthanides have fairly high melting and boiling point. However, the melting and boiling point do not show any regular trend as we move from lanthanum to lutetium in the series. Inspection of table 4.2 shows the europium and ytterbium have unexpectedly low melting and boiling point. These atoms form EU2 positive and YB2 positive ions result in weaker metallic bonding because there are less than 3 electrons per atom in the metallic bonds. The other lanthanide atoms give 3 electrons per atom in the metallic bond. Therefore, melting and boiling point of europium and ytterbium are low as compared to the value of the other lanthanide element. Next point is density. The density of lanthanides are low, which ranges between 6.7 to 9.74 gram per centimeter cube. However, there is no definite trend in the density values of lanthanides with increase in atomic number. Europium and ytterbium have unexpected low values. And the next point is heat of fusion and heat of vaporization. It's also do not show definite trend with increase in atomic number. Electronegativity value. The electronegativity value of lanthanides between 1.0 to 1.15 are quite close to those of alkali and alkaline earth metals. Therefore, lanthanides are expected to form ionic compounds. Next is electropositive character. Because of low ionization energy and electronegativity values, the lanthanides are electropositive like S block elements. Third, oxidation states. The common oxidation state of all the lanthanide is +3. In addition, some lanthanides show +2 and +4 oxidation state also. These are shown by those elements which by doing so attain the stable F0, F7 and F14 configuration. Ce and Tb exhibit +4 oxidation state. Cerium and terbium attain F0 and F7 configuration respectively when they get +4 oxidation state as shown below. Europium and ytterbium gets F7 and F14 configuration in +2 oxidation state. LAGD and Lu exhibit only +3 oxidation state. These elements show +3 oxidation state only because by losing 3 electrons. They acquire stable configuration of empty, half-filled and completely filled for F subshells. Exceptional examples. Some other elements show +2 and +4 oxidation state even though they have electronic configuration other than F0, 7 and 14. For example, Sm and Tm show +2 states having F6 and F13 electrons respectively, in which they have 1 electron less than half filled or completely filled configuration. Similarly, PR, ND and DY show +4 oxidation state having F1, F2 and F8 electronic configuration. The stability of these unusual oxidation states may be dependent upon some other thermodynamic and kinetic factors which are of significant importance, but these are less stable than the +3 oxidation state which is characteristic of this family. The outer electronic configuration of lanthanides in different oxidation states are given in table 3. Outer electronic configuration of lanthanides in different oxidation states. Color and spectral properties. The lanthanides are silvery white, but many lanthanide ions are colored both in the solid and in the aqueous solution. The colors remain same even on the change of anions. Therefore, the colors are characteristic of the lanthanide ions. The color of the ions depends upon the number of the unpaired electrons because it has been observed that the ions containing NF electrons have almost similar color to those with 14 minus NF electrons. The different ions having NF and 14 minus NF and their colors are given in table 4. Color of lanthanide ions. Lanthanide 3 positive is colorless, Ce3 positive is colorless, Pr3 positive is green, Nd3 positive is lilac, Pm3 positive is pink, Sm3 positive is yellow, uh, Eu3 positive is pale pink, and Gd3 positive is colorless. Lu3 positive is colorless, YB3 positive is colorless, TN3 positive is pale green, AR3 positive is pink, HO3 positive is pale yellow, DY3 positive is yellow, TB3 positive is pale pink. However, it has been observed that some di and tetrapositive ions having same number of electrons as tripositive ions do not have same color. Sm2 positive and Eu3 positive have same number of unpaired electron but they have different colors. Some other examples are given in table 5. The color of the lanthanide ions arise due to absorption of light from visible region of the spectrum resulting in the electronic transition within the 4f level FF transition. A remarkable characteristic of the spectra of the tripositive lanthanide ions is that the absorption bands are extremely sharp line like bands in ultraviolet, visible or near infrared region. Many of these bands are line like and become even narrower as the temperature is lowered. This behavior is in contrast to absorption bands of DD transitions which have broad absorption bands. The bands of lanthanide ions are sharp that they are useful for characterizing the lanthanide ions. The main reason for very sharp absorption band is that the 4f orbitals lie deep in the atoms of these elements. Therefore, they are effectively shielded from the surroundings by the overlying 5s and 5p orbitals, and consequently, the absorption bands arise mainly from the electronic transition within the 4f levels. The absorption bands show little dependence on the nature of the ligands. In addition to FF transition, sometimes color of lanthanide ions is also attributed to FD transition. The FF absorption transition of lanthanide ions have low intensity because they are not allowed, whereas FD transition are allowed. In contrast to FF transition, the FD transition are allowed and hence show very intensive absorption bands. For example, the FD transition observed for Ce3 positive and Tb3 positive are very intense. Magnetic properties. All the lanthanide ions with the exception of La3 positive, Lu3 positive, Ce4 positive and Yb2 positive ions are paramagnetic because they contain unpaired electrons. In their 4f subshell, the ions La3 positive, Lu3 positive, Ce4 positive and Yb2 positive which have 4f0 and 4f14 electronic configuration are diamagnetic because they have no unpaired electrons. The magnetic properties of the lanthanides are different from those of the transition elements. As we know, the magnetic moment arises from two types of motions of the electrons. The spin motion of electron around its own axis produces magnetic moment called spin magnetic moment, while the orbital motion of the electron around the nucleus produces magnetic moment called orbital magnetic moment. The observed magnetic moment of a substance is due to the contribution of both the spin moment and the orbital moment. In case of transition element, the magnetic moment mainly corresponds to the spin only magnetic moment. This is due to the fact that the d orbitals are not well shielded from the environment and take part in bond formation with the ligands. As a result, the d electrons of the metal interact strongly with the ligands surrounding the metal ion. Due to the electric field of the ligands, the orbital motion of the electron get restricted and thereby the orbital moment of these electrons get quenched. The magnetic moment of d block elements thus arises mainly from the contribution of spin motion of the electron only. The spin only magnetic moment is given as by the formula under root n into n plus 2, where n is the number of unpaired electrons. This relationship gives almost correct values of magnetic moment for d block elements. However, the above relationship is not valid in the case of f block elements. In these elements, the 4f orbital are well shielded from the surrounding by the overlying 5s and 5p subshell. As a result, the electric field of the ligand surrounding the metal ion does not restrict the orbital motion of the electron. Thus, orbital contribution is not quenched. Therefore, the magnetic moment of the lanthanide ions is due to both electron spin and orbital motion of the electron. Is calculated as under root 4s into s plus 1 plus l into l plus 1. whereas is the resultant spin quantum number and L is the resultant orbital momentum quantum number. The theoretical and experimentally observed magnetic moment values are given in table 4.6. The magnetic moment of lanthanide depend upon the atomic number and the number of the unpaired electrons. For the ions Le3 positive, GD3 positive, Lu3 positive, the magnetic moment correspond to spin only values. As we can see that from the table, theoretical and experimental values. The magnetic moment of tri-positive lanthanide ions are plotted in figure 1. La3 positive and Lu3 positive are diamagnetic, no unpaired electrons. It is observed that the value increases up to neodymium and then decreases to 1.474 Sm3 positive ions. It increases again and reaching a maximum value for dysprosium and holmium. Thereafter, it starts decreasing and becomes zero for lutetium, which is diamagnetic. The unusual shape of the next is ionic radii and lanthanide contraction. We know that as we move down a group, atomic size normally increase. This is mainly due to the additional cell of electron or electron between the successive periods. However, as we move across a period from left to right, atomic size decrease. This is attributed to the increasing effective nuclear charge, as a result of which the outermost shell of electron is attracted more and more. Consequently, the size decreases. For example, the covalent radii of alkali metals increase from Li to Cs and for halogens from F to I. If we consider the ionic radii of lanthanide, we get very interesting observation. For comparison sake, we can take the ionic radii of trivalent ions M3 positive, which are most stable. These are shown in figure 2. It is clear that ionic radii decrease from one element to the another in the lanthanide series, but decrease is very small. It has been observed from C3 positive to Lu3 positive. The ionic radii decrease from 1.03 angstrom to 0.86 angstrom. Obviously, for an increase of atomic number 14, the decrease in ionic radii is only 0.17 angstrom. This is very small decrease in the comparison to element of other groups and periods. Similarly, on moving from Ce to Lu, the atomic radii also decrease from 1.65 angstrom to 1.56 angstrom, and the decrease is only 0.09 angstrom. This small steady decrease in ionic or atomic size of the lanthanide elements with increase in atomic number is called lanthanide contraction. Cause of lanthanide contraction. In lanthanide series, the 4f electrons are being added one at each step as we move from one element to another. The shielding of one f electron by another from the nuclear attraction is quite weak due to the shape of the f orbital. The nuclear charge, however, increases by 1 at each step. Hence, with increasing atomic number and a nuclear charge, the effective nuclear charge experienced by each 4f electron increase. Hence, the inward pull experienced by the 4f electron increases, and this causes a reduction in the size of the atom. The sum of the successive reduction gives the total lanthanide contraction. Consequences of lanthanide contraction. Lanthanide contraction has very significant effect on the relative properties of the elements which precede and which follow the lanthanide in the periodic table. Some important consequences of lanthanide contraction. Steady decrease in size. There is a regular decrease in the ionic radii of lanthanide. Next is electronegativity. There is slight regular increase in the electronegativity of the trivalent ions. Electrode potential values. There is a small but smooth increase in standard electrode potential values. E note for the process. For lanthanum is minus 2.52 volt to minus 2.25 volt for lutetium. Resemblance of second and third transition series. The lanthanide contraction affect the chemistry of second and third transition series. As we can see from table 8, there is regular increase in size from scandium to ytterbium to lanthanum. Similarly, we expect normal increase in size in other groups. However, after lanthanide, the increase in radii from second to third transition series almost vanished. The pair of electrons ZRHF, NBTA, MO, W, etc. poses almost the same size. The properties of this element are also very similar. Next point is similarity among lanthanides. Because of the very small change in the size of the lanthanide ions in lanthanides, their chemical properties are similar. Therefore, their separation becomes very difficult. Recently, methods based on the repeated fractional crystallization or ion exchange techniques, which take the advantage of slight differences in their properties like solubility, complex ion formation, hydration, etc., arising from very slight size difference of their trivalent ions have been used. The next point is basicity differences. Due to lanthanide contraction, the size of the lanthanide ions decrease regularly with increase in atomic number. As a result of decrease in size, their covalent character between Ln3 positive ions and OH negative ions increase, and therefore the basic strength of the hydroxide decrease with increase in atomic number. Thus, LaOH3 is the most basic while LuOH3 is the least basic. The basicity differences in lanthanide are reflected in increasing tendency to get hydrolyzed. Due to decrease in basic character, there is slight increase in degree of hydrolysis in solution from lanthanum 3 positive to lutetium 3 positive. Li3 positive ions are less readily hydrolyzed than Lu3 positive ions. Thermal decomposition of oxysalt. More basic oxysalt decompose less readily. LaNO3 thrice decompose with difficulty and is stable, whereas LuNO3 thrice is unstable and decompose readily. Next is size of the ytterbium and HO and dy. Due to lanthanide contraction, the radii of YB3 positive is comparable to heavier lanthanides that TB, DY, HO and ER. Therefore, they occur together in natural minerals. Next point is reactivity of lanthanides. All the lanthanide are highly electropositive metal and have almost similar chemical reactivity. This is due to the fact that the lanthanide differ only in the number of 4f electrons. Since these electrons are very effectively shielded from interaction with other elements by overlapping 5s and 5p and 6s electrons, they show very little differences in their chemical reactivity. Because of their similar chemical reactivities, their separation from one another is very difficult. The lanthanide in general more reactive than d block element. Some of their chemical characteristics are: they tarnish readily on exposure to air. In a finely divided state, all burn in air to form sesquioxide of the formula Ln2O3, where Ln stands for lanthanide, except cerium, which gives CeO2. Ytterbium, however, resists the action of air even at 1000 degrees Celsius due to the formation of a protective coating of its oxide. Second point is all react with water slowly in cold but rapidly on heating, liberating hydrogen and forming LNOH thrice. Next is all these combine with hydrogen at 200 to 300 degrees Celsius, giving LNH3. And the next point is they also combine with halogens, oxygen and sulfur. Next point, they act as strong reducing agent for oxides of other metals. Cerium is used as a scavenger of oxygen and sulfur in many metals. They react with nitrogen to form nitrides of the formula LNN. Solubility of the compounds: fluoride, oxide, hydroxide, carbonate, phosphate, chromate, and oxalates of lanthanide are largely insoluble in water. On the other hand, the halides other than fluorides, nitrates, acetates, perchlorates, and salts of oxoacids of lanthanides are soluble in water. The solubility behavior of salts of lanthanides follow the pattern of solubility of salt of group 2 elements. However, the lanthanide sulfates, unlike the sulfates of group 2 element, are soluble in water. Tendency to form complex. Although the lanthanide ions have a high charge +3, yet they have large size of their ions. As a result, they have low charge density and therefore they have very less tendency to form complex. Their complex with unirandate ligand are very few and form complex only with fluorine and oxygen donor ligands. However, they form complex with a few chelating ligands such as oxime, ethylene diamine tetraacetic acid EDTA, and acetic hydrocarboxylic acid such as citric acid, etc. These complexes usually have high and variable coordination number, and water or solvent molecules are often attached to the central metal atom. Beta diketone complex of EU3 positive and PR3 positive dissolved in organic solvent are used as lanthanide shift reagent in NMR spectroscopy. In contrast to transition element, the coordination number 6 is not very common. Coordination number below 6 is also uncommon and occur only with bulky ligands such as 2,6-dimethylphenyl ligands. However, coordination number 7, 8, 9 are common in, and these give a varieties of stereochemistries. For example, the coordination number for LNOH twice N3 positive in aqueous solution are thought to be 9 for early lanthanides and 8 for later smaller members of the series. However, these ions are highly labile. The smaller ytterbium ion Ib3 positive forms 7 coordinated complex and larger La3 positive is 8 coordinated complex, where AC is acetyl acetonate. The structure of these compounds are a capped trigonal prism and a square antiprism are shown in below. Figure 3 coordination number 10 and 12 occur with the larger lanthanide and small chelating ligands such as NO3 negative and SO4 2 negative. Ce4 positive is smaller and highly charged and form CeNO3 6 2 negative in the non-aqueous solvent N2O4. This is 12 coordinated Ce in which each NO3 negative uses two oxygen atoms to coordinate to the metal. When two trans nitrate of this complex are replaced by PH3PO, it gives 10 coordinated orange colored neutral complex. The sulfate and the iodates are also known. Large number of salt of organic acids such as oxalic, citric, and tartaric have been studied mainly for the separation methods. These anions have chelating O ligands forming complex with the LN3 unidendate O donor such as pyridine N oxide and triphenyl phosphide oxide also form. Many complex with lanthanide in plus 3 oxidation state. Complexes with ligands such as and diene, pi, and terpi can also be prepared in polar organic solvent. For example, coordination number of 8, 9, 10 are typical examples. As with other transition metal, the lanthanide can be induced to form complex with exceptionally low coordination number by use of bulky ligands such as an SiMe3 twice negative. This is an example of coordination number 3, which is the lowest found for lanthanide. They are volatile, air sensitive, and easily hydrolyzed. They are planar in solution but pyramidal in the solid state. With PH3PO, the four coordinated distorted tetrahedral adducts are formed. Lanthanide also form two main types of organometallic compound, predominantly ionic cyclopentadienides and sigma bonded alkyl and aryls. These type of compound are usually thermally stable but unstable with respect to water and air. The series and salt containing C5H5 negative anion are readily prepared by the reaction of anhydrous LnCl3 and NaC5H5 in appropriate molar ratio in THF. In polar solvent, these complexes are solvated and are monomeric, but in non-polar solvent, the trace C5H5 compound are insoluble, while the bis C5H5 compound dimerize the lanthanide also form alkyls and aryls by metathesis in THF or ether solution. LnCl3 plus 3 LIR gives us LnR3 plus 3 LiCl. LnCl3 plus 4 LIR gives us LNR4 plus 3 LiCl3. Triphenyl are polymeric in which Ln is tetrahedrally coordinated to 4 sigma aryl groups. Methyl derivatives have also been obtained. Octahedral species of lanthanide have been isolated. In contrast to transition element, the lanthanide do not form complex with pi bonding ligands such as CO, NO, CNR, etc. The difference arises because of the 4f orbital are well shielded and are inside the atoms. Therefore, they can't take part in pi bonding, whereas in the transition element, the d orbital are commonly involved in pi bonding. Double salt formation. The lanthanide salt form double salt with corresponding salt of ammonium and alkali metals. Double salt like alums with 24 water molecules are not formed. This is because the lanthanide ions are so large that these cannot coordinate to 24 water molecules octahedrally as in alums. Occurrence of lanthanides. Although lanthanide were originally called rare elements, the recent studies have shown that these are not rare. All the lanthanide except promethium occur naturally. Some of them, particularly cerium, lanthanum, and neodymium, are very common and occur in fairly large quantities. Cerium is the 26th most abundant of all elements. It has been observed that lanthanide having even atomic number, are more abundant than their neighbors with odd atomic number. There are about 100 minerals known to contain lanthanide. The main mineral are monazite. It is the most abundant and most widespread mineral, account for about 78% of the lanthanide mined. It is a mixture containing La phosphate and trivalent phosphate of the lighter elements such as CePr and D. It also contains small amount of heavier element and thorium phosphate. This mineral is contaminated with other similarly concentrated minerals such as ilmenite and cassistrite. And the next is bastnasite. It is a mixed fluorocarbonate M3CO3F, where M is a La or lanthanide. The contribution of the metals in monazite and bastnasite is almost similar, but the difference is that monazite contain around 5 to 10% TiO2 and 3% ytterbium, earth, which are virtually absent in bastnasite. Large amount of bastnasite minerals are found in California, Sweden, New Mexico, etc. Third is cerite. It contains silicate of cerium, LAPR, ND, and SM. It is found in Norway and Sweden. In addition to above three main minerals, many other minerals in small amounts are euxenite containing CeNbTh ytterbium earths, and the xenotime containing ytterbium and Th, and Kurthite containing double silicate of cerium, and gadolinite containing ytterbium earth and Ce and Th. Isolation of lanthanide. Monazite is the best known mineral containing the lanthanide. It is a mixture of phosphates, LnPO4 containing thorium, zirconium, iron, and titanium silicate. The mineral is powdered and digested with hot concentrated H2SO4 until a paste is obtained in which the phosphorus change into the corresponding sulfate. The paste is separated by centrifugation and treated with cold water, the sulfate being more soluble in cold water than by centrifugation and treated with cold water, and the sulfate being more soluble in cold water than in hot water pass into the solution, while silica and zircon etc. being insoluble are removed. The solution is neutralized with NH4OH when thorium, zirconium, and titanium are precipitated out as phosphate. Then the solution is treated with the sodium sulfate with precipitate out La, and light lanthanides are as double salt, while the heavy lanthanides still remain in the solution. The precipitated double salt of light lanthanide are treated with hot sodium hydroxide solution when they are converted into a mixture of oxide and hydroxide. The mixture is washed to remove sodium sulfate formed during the process and dried in air at 100 degrees Celsius. In this process, cerium is completely oxidized to CEO2 and the other lanthanides are changed as oxides Ln2O3. The mixture is treated with dilute HNO3 so that all lanthanide oxides except CEO2 dissolve. The CEO2 is left as residue and is filtered. The crude CEO2 is dissolved in 85% HNO3 and added to an excess of dilute H2SO4, whereby the cerium is precipitated as red basic nitrate CeOH, NO3 का thrice and 3H2. After the removal of Ce, the other light lanthanide are separated into individual components by different methods based mainly on solubility differences. Method for separation into individual elements. The properties of metal ions are determined by their size and charge. All the lanthanide ions are trivalent and have almost same size so that their properties are almost identical. Therefore, the separation of lanthanide from one another is very difficult. Recently, method based on repeated fractional crystallization, ion exchange techniques, etc., which take advantage of slight differences of properties like solubility, complex ion formation, and hydration, arising from very slight differences of their individual trivalent ions have been used. These methods are discussed below. First, repeated fractional crystallization. Simple salt of lanthanide such as nitrate, sulfate, bromate, oxalate, as well as double salt like 2LaNO3 thrice dot 3 MgNO3 twice dot 24H2O form well defined crystals. The solubilities of these salt decrease from lanthanum to lutetium by repeating fractional crystallization a number of times. The individual components can be obtained During fractional crystallization, the less soluble salt will be obtained first and the most soluble salt will be obtained last of all. By repeating the crystallization process, the less soluble salt will be accumulated more and more in the crystals, and the mother liquor will contain more and more of the most soluble salt. This method has now been improved by the use of non-aqueous solvents such as ether. Second is fractional precipitation. When only a small amount of precipitating agent is added to a mixture of lanthanide salt, the substance having the lowest solubility product will precipitate most rapidly and most completely. For example, if solution hydroxide is added to a solution of the lanthanide nitrates LUH thrice, which is the weakest base and the lowest solubility product, is precipitated first, while LUH thrice, which has the highest solubility product, is precipitated last. A partial separation takes place in this manner. By redissolving the precipitate and then precipitating again a number of times, it is possible to have a complete separation. And third point is solvent extraction. The partition coefficient of the salt of these metals between water and organic solvent are slightly different. Therefore, these can be extracted by using different solvent and repeating the extraction process again and again. For example, the partition coefficient of GDNO3 thrice between water and normal butyl alcohol is 1.06 times greater than that of the LaNO3 thrice. This means that GDNO3 thrice can be separated from LaNO3 thrice by continuous extraction with water from a solution of these salt in butyl alcohol. Sheet diagram for the extraction of lanthanide elements. We can see in this. Next point is change of oxidation states. Some of the lanthanides show +2 and +4 oxidation state in addition to the +3 state, which is most characteristic of all the lanthanide. The property of the M2 positive and M4 positive ions are different from those of the usual N3 positive ions. For example, the cerium can be separated from a mixture of trivalent ions of all the lanthanides by oxidizing it to cerium 4 positive state. By reacting it with alkaline KMnO4, Ce4 positive ion has a greater nitrate changes to oxide. Therefore, heavier nitrates decompose first while light lanthanide nitrate decompose last. The process of decomposition of nitrate is at different temperature is carried out, and the oxides separated at each stage are then dissolved in HNO3. Ion exchange method. This is the most useful and most efficient method for the separation of lanthanide. Generally, a column of synthetic ion exchange resin with acid functional group such as ZOH, SO3H is used. The solution containing the trivalent lanthanide ions is passed through the column when the hydrogen ions are replaced by the metal cations. The column now contain as the lanthanide ions fixed onto the resin in order to recover them. The column is eluted with a citric acid ammonium citrate solution. In the first stage of the ammonium ions replace the lanthanide ions. The ions which are bound least firmly to the resin are displaced by the ammonium ions first, while those are bound most firmly are replaced last. The firmness with which the lanthanide ions are fixed to the resin depends upon its size. The smaller the size of the lanthanide ion, the more firmly it is bound to the resin, and vice versa. Since lanthanide ions are present as a hydrates, the firmness depends upon the size of the hydrated ion. Smaller ion is hydrated to a greater extent. Therefore, the smallest lanthanide ion will be most heavily hydrated, while La3 positive ion, being largest, will be hydrated to the minimum extent. The size of the hydrated La3 positive ion is the smallest, and therefore it is attached to the column and maximum with maximum firmness. On the other hand, Lu3 positive ion is attached with the minimum firmness, and firmness decreases from La3 positive to Lu3 positive. Thus, Lu3 positive ion is eluted first, while the La3 positive ion is eluted last. And the next M3 positive plus citrate ions gives us M citrate complex. By complex formation, lanthanide oxalates are insoluble in water, but they can be dissolved by complexing with ethyl diamine tetraacetic acid (EDTA). These complex differ in their stabilities towards acid. The least stable complex is destroyed first and changes to the oxalate, while the most stable complex is destroyed last on the addition of an acid. Production of metal. First, the electrolysis of the fused chloride, and the second, electrolysis of CEO2 infused CeF2. This method is used in the production of cerium and is similar to the method used in metallurgy of aluminium. Third, reduction of anhydrous chloride with sodium. The reduction takes place at a high temperature above 1000 degrees Celsius. The method is used for production of lighter lanthanide such as LaCeGa. LaCl3 plus 3Na gives us at 1000 degrees Celsius temperature La plus 3NaCl. Fourth is reduction of anhydrous fluorides with calcium or magnesium. This method is used in the production of heavier lanthanide because the fluoride are less volatile than the chloride. The loss of evaporation therefore small when fluoride are used instead of the chloride. The reduction is carried out at temperature above 1000 degrees Celsius. 2LuCl3 plus 3Mg gives us at 1000 degrees Celsius 3MgCl2 plus 2Lu. Lanthanide compound. The lanthanide compounds are soft and silvery white. They are electropositive and they are reactive. They react with hydrogen forming the hydride of the composition LNH2 and LNH3. These also react with the several other non-metals including oxygen, halogen, sulfur, nitrogen and phosphorus, carbon, silicon, etc. Most of the lanthanide compounds are known in plus 3 oxidation state. However, some compounds of lanthanide in plus 2 and plus 4 oxidation state are also known. The important lanthanide are oxide and chalcanogen, chalcogenides. Only CEPR and TB and NB form oxide in plus 4 oxidation state. CEO2 is pale yellow inert material when prepared by ignition. However, in the hydrous, freshly precipitated form, it is dissolved quite readily in acids. The analogous dark colored PrO2 and TbO2 are obtained from their stable oxides PR6O11 and TB4O7 under extreme condition. Lanthanide burned with oxygen forming the oxide Ln2O3. These are also obtained by ignition of hydroxide, carbonate, nitrate. Ln2O3 are well characterized. 2Ln plus 3O2 gives us Ln2O3. Ln2O3 adopt three types of structures: A type, B type, and C type. A type, these consist of LnO7 unit which have approximate to capped octahedral geometry. And B type, these consist of LnO7 unit which have capped trigonal prism and capped octahedron geometry. C type, these have fluoride structure in